I'll say a few words in Hebrew first, opening words, and then all the talks will be in English. אז ברוכים הבאים כולם, אנחנו במקור היינו צריכים להיות פה בסוף אוקטובר לפי התכנון, אבל לצערי היינו צריכים לדחות, וכיף שאנחנו חוזרים למיטאפים. עכשיו יש הרגשה כזאת שכל יום יש כמעט מיטאפ מעניין בתל אביב, היום יש גם בירושלים במקביל מיטאפ, ובטח גם בחיפה. אז קוראים לי קוסטה קילימניק, אני מוביל בתי ספר של דאטה בחברת מאסטר סקול, ובזמן החופשי שלי עוזר לארגן את המיטאפים ולקדם את הקהילה של מערכות המלצה בארץ. המטרה שלנו לעשות יותר ויותר מיטאפים ואולי גם מעבר למיטאפים. היום יש לנו 3 הרצאות מגוונות, כולן מאוד מעניינות, גם חלק מעשי, גם חלק יותר תיאורטי, אז אני בטוח שאתם תהנו. ואני נותן מיקרופון לברכה להגיד כמה מילים גם על הקהילה.
היי, אז אני ברכה שפירה, אני מאוניברסיטת בן גוריון ומאי-ביי. אז קודם כל באמת התרגשות לראות כל כך הרבה אנשים אחרי כמה חודשים, כמו שקוסטיה אמר, שככה הקהילה התחילה לצמוח, אז באמת כיף, ותודה רבה לקוסטיה על כל העבודה שהוא עושה ממש בארגון של זה, ותודה רבה לטאבולה ששוב מארחת אותנו, ממש כיף להיות כאן, ותודה לאי-ביי גם על התמיכה כמובן, הקהילה באמת הצטרפו, היא כבר כמעט 700 איש, ואנחנו, אם יש פה חברות שרוצות לארח בפעם הבאה, אתם מוזמנים לפנות אלינו, ויאללה, שיהיה מעניין. תודה רבה.
תודה ברכה. יבגני, בוא תגיד כמה מילים בפינה של ההוסט.
פינת ההוסט. היי לכולם, תודה שבאתם. זה באמת רק כמה מילים. אז אני יבגני ממחלקת האלגוריתמים בטאבולה, אנחנו מאוד שמחים לארח אתכם כאן, שמחים שבאתם, תודה לדניאל, חי ואורי שבאו ומציגים דברים, ואני מקווה שיהיה מעניין ותהנו. תודה רבה.
תודה יבגני. Okay, so let's start with our first talk. Daniel. Okay, the microphone is yours and you have the clicker.
Thank you very much. So this is the next one, right?
Yes.
All right. So first talk, actually all the talks in English, so thanks for accommodating the foreigners. Hey everybody, my second week in Israel, so all the questions should be nice and at the end of the talk, preferably. And we'll talk about building recommender systems and user modeling systems with vector embeddings, which you might ask yourself, is there any other way to do it? And the answer is no. And you know, the difference is only in how difficult you make it for yourself. So hopefully we find a way to do it so that even an engineer can do it, right? Okay. Quickly about myself, my background is in engineering. I did a little bit of algorithm research, but mostly I would say I'm an engineer. I spent some time at IBM Research and building machine learning infrastructure for YouTube ads. I co-founded Superlinked in 2021 with Ben, who sits over there. And we have been working with Eli, who is over there for the last 6 months. He's our first local hire in Israel. And we are actually growing the local presence by maybe 3-4 engineers over the next few months. So mainly this is a kind of a recruiting pitch, but hopefully we'll also learn something. And we have kind of experimented with building recommender system infrastructure for a few years. And last year, what crystallized out of that work was what we call a vector computer. And it's a system focused specifically on encoding complex data into vector embeddings. and then having a clever way to formulate search objectives within these ensemble vectors that encode these complex entities. And the use cases go beyond RecSys into search and analytics and so on. And so that's what we are focusing on now. If you go on the website, you'll find a link to the GitHub. The product is open source, free to use, always looking for feedback. So that's briefly my background and what we do. This clicker is not exactly real time. So just, for the folks out there who have not been in contact with vector embeddings as a way to represent knowledge, all your favorite kind of content discovery systems out there already ran on vectors for many years. And there are many companies, most likely including Tabula, that build custom models to encode their content and user preferences as vectors. So this is nothing new. And the question now is, can we help kind of the rest of the industry work with vectors? Can we make it easier for them? Because it seems to clearly work. I have one stat, which is that in 2020, already back then, 10% of Google.com searches were powered by a vector search index, not by the reverse keyword lookup. So, worth looking into the technology if you haven't already. And then, most likely some of the tools that you need are already part of your existing data stack. So most likely the database that you use today, be it Postgres or BigQuery or anything in between, already supports you putting in vector embeddings and the database building an index that helps you find similar ones quickly, right? So if you encode your items and your users into the same space, then the database can, for a given user, find you the relevant products, for example, right? And this already you can use probably your existing database. This URL is a crowdsourced comparison of all the databases that might be out there. We have 37, I believe, currently on there. And basically the community filled in the support for the different features, hybrid search and offloading of the disk of the index on the disk and open source license and all of those considerations. We have a website that if you are looking to choose your vector database, that's a good place to check out. We just, I think, a couple days ago launched Rust grade pools as statistics. So if you are into Rust, now you can know which vector database is popular in the Rust community, if you cared about that. We also have, npm pools and Docker Hub pools and GitHub stars and all that good stuff. Okay. Now, let's talk about a specific use case and let's run through an example of how we delivered a recommender system for a UK-based e-commerce business with about 2 million users, 5 million monthly visitors, and $133 average order value, using vectors and keeping everything nice and simple and not building models from scratch, for example. So that's the case study, and from this picture you can tell that it's kind of, let's say, high fashion marketplace, fairly large. So what did we do with these guys? There are 6 different surfaces within their website that are useful to be personalized, from the homepage and for you feed and the cart. Once you add a bunch of items into cart, you can suggest complementary items. There is also the 100 million emails they send every month. Those can be personalized. So the scope of the problem is that, let's say, if you are building in the traditional sense a ranking model for each of these different surfaces, that's 6 models right away, a lot of work, right? So in these kind of scenarios where, and that doesn't even count the mobile app and other areas, and so for that, you have to have some plan for how maybe you don't build the ranking model for each of the different places where you want to show the recommendations. Again, simplicity is key. But this gives you some idea of what the screens look like and what kind of products appear and how important, for example, the image is for the description of the product and so on. So these are some example of the places that we already ran 50% A/B test with them, and there is a couple more. And so these are the results, just to kind of motivate ourselves to even care about this. So one big requirement was that this specific brand has a very quickly changing product catalog because things go on sale, or they have very few available items from each item. And then so if somebody buys them, you want to stop recommending them immediately. And so end-to-end update latency when the product goes out of stock to the product no longer being surfaced to user should be on the order of seconds, ideally. And then, for the recommender system people out there, one of the classical problems is the cold start, right? So before you have enough data about an item or a user, what do, right? So you have to somehow incorporate the content features, the description of the product, maybe some preference the user expressed during sign-up. So we had to take care of that aspect as well. The whole project took about 2 months to integrate and tune and, let's say, launch. It's a 50% A/B test. So for 50% of the users, it launched, basically. And from the data that we see so far, we have about over 10% of revenue lift on the surfaces that we power, which for this specific brand that makes, let's say, low 9 figures of revenue, it's a decent amount of money, let's say. And then, as engineers, if we can price our product as some fraction of this value that we create for our customers, that's good. You can build a company this way. Cool. So let's just kind of look at the system before we brought the power of vectors into it. So quite classical setup, right? You have a product database that hosts all the product metadata, the product catalog. There was about 500,000 products, or is about 500,000 products. You have all the user events, right? What are people clicking on and adding to the basket and so on. You have the database of users. So most of the traffic on this particular platform is signed in, which is really good for us recommender system people, because there is a lot of user history. And then there is some kind of content management system where before we started to work with the company, there was 10 plus people manually managing bundles of products and sales and kind of babysitting the user experience from that point of view, informed by some kind of business intelligence solution that gave them insights into what sells in which geographies and user segments and so on. So this is quite sort of classic setup, right, where humans have a lot of control, right, but nothing is personalized, basically, right? So that's kind of the starting point in many of these projects. And then the main search experience was powered by Algolia, which many of you probably know. Algolia is great, but for example, the update latency is not sub 5 seconds. So that's one consideration. So this is the before picture. And the after picture looks a little bit like this. We basically we worked with a company called StreamCap, which is a partner of ours, and what they do is they collect various data sources and join the data and make it easier to work with. From there, the user events and product updates and user metadata from the user database is funneled to Superlinked, to our system, and Superlinked turns this data or uses this data to update the embeddings of the products and the users. And then from there, the underlying index for these vectors to do the similarity search for this project was Redis. Redis has been working with us for the last 3 years or so. When we looked at the vector database market those 3 years ago, they had a really good update latency for the index, which not that many people look at. So really great partner. And then from there, once you index all the user vectors and all the product vectors, we have a set of APIs that help the manual content management to find complementary products, but also directly power the experience on the website across those different surfaces. We also work with Rubber Ducky Labs, which was funny to see the rubber ducks on the entrance, which is a company that works on RecSys analytics, right? So if you have your Looker dashboard or general business analytics tool, and you are trying to use it to understand your recommender system, I suggest reaching out to Rubber Ducky Labs. Sorry? For recommender systems. Yes. They are let's say, BI solution for recommender systems. That's right. Cool. Any questions for this? StreamCap is a kind of like managed Kafka, a solution that helps you plus transformations also. So they have an ability to pull from a bunch of sources, join, transform, and send the data onwards. And for us, it means we don't have to integrate with a bunch of different sources, right? We have a connector integration. Yes. How does Superlink work with Redis? No, Redis has a vector search index. Yeah, they have it available through a module. So within Redis search, there is a vector search offering there. Part of the team that builds that, by the way, is also based in Israel. So I'll dive a little bit deeper into the Superlink box. How am I doing on time? Meanwhile, okay, very good. Okay, so just kind of zooming into that Superlink box. Okay, there is like all the data goes there, and then the recommendations come out. So that seems like that's the interesting part. So in this picture, it's in the middle, and then the vector index is at the bottom. And then the question is, the data that feeds it, broadly, we can put into two categories, right? We have the structured data. Let's say these are the user clicks and the specific category IDs of the products, that sort of stuff. Product prices, product availability. And then we have the unstructured data, which is mainly the product description and the product image, right? And somehow, if you want your vectors to encode everything you know about the users and the products, you have to find a way to integrate those two types of data into one encoding, right? So this is the challenge. And then somehow, you need a set of APIs that then power the actual searching. Okay. Now, if you kind of imagine what a product is in an e-commerce sense, it probably has a bunch of different parameters, right? As I said, there is probably image, some text, and other properties, and you need to find a way how to encode all of this into a fixed array of floating point numbers. That's the challenge, right? Our framework right now has the ability to combine text, image, scalar, categorical, and timestamp properties and bring them all into the actual encoding. So you can have, let's say, dense embedding of the description, and then 20 dimensions used to encode the timestamp when the document was created. And then at query time, you can do smooth trade-off between relevance and freshness in that example, right? Of course, in practice, you want to encode all kinds of different things and navigate the trade-off across all those different properties. In our roadmap, we are working on time series. So let's say you have a pricing history of a product. You want to be able to use that to discover which products are similar or similarly sort of periodical in terms of their sales. You'll be able to do that. And then, of course, graph data, products can be related to each other through the interactions or through their presence in categories. So that's also on our roadmap. I have a quick example of how the code actually looks, but for people who are interested in that, you can just go to our GitHub. We have about 20 different notebooks that go into detail of how the framework works. One way to imagine it is basically like we used to have ORM systems, right, for object relational mapping. We're thinking objects under the hood, data saves in the relational table. What we do is kind of OVM, right? You think in objects and the underlying system is vectors, right? So you kind of create your data schema and you define how the different properties get embedded, and you build indices from that. And then at query time, as I said, you can navigate between, let's say, relevance and recency, and set the weights at query time, right? So you can do an A/B test of, on different parts of your website. Maybe recency is more important than personalization, right? And you can decide this at the very last moment when you run the query without recalculating the index. That's important. So it's a Python framework, as you can see, kind of declarative, easy to use. And then we also make it easy. This part is not yet in the repo, but soon will be, and it makes it easy to deploy, right? So when you figured out in a Python notebook, okay, here's how I want to encode my data, here's how I want to run my queries, we then make it easy to run a service in your cloud account that connects to a vector database on the backend and auto-generates ingestion and query APIs, and then you can use it to power your e-commerce shop. Cool. So just a quick summary. We have actually raised $9.5 million last year from US-based investors. I'm personally based in San Francisco, but we have presence here and in London and in Budapest. We are hiring, so you can connect to me through that QR code or find me after the talks. Very happy to chat. And yeah, we have announced partnerships with Mongo, soon announcing partnership with Redis, Dataiku, Starburst. So our goal is to partner with everybody and add the vector making capabilities to their infrastructure products. Thank you very much.
Any questions? We have some time. Database all of them. Why you can just easily place your website a good example of the usage of Kubernetes just to short profile of the company and the best recommended.
So vector index of vector databases. It's perfect. You can contribute. You can send us a pull request. No, we might consider it. Thank you.
Yes.
Yep.
How do you encode things like the probability of Google license? If you see something not right, then see something other way.
Mm-hmm.
If you want to recommend items that people are likely to buy, and avoid items that are unlikely.
Yeah. So yes. How do we encode the probability of a user buying an item without training the embedding model and kind of back propagating that error into the model, basically? Well, the expectation is that the pre-trained models will project users that are likely to buy something near the product projection, right? So there is some expectation that the positions in the embedding space correlates to the probability of purchase as a baseline, right? And then the question is, how do you kind of refine this, right? So easy way to do that, for example, is to, without training a model, and by the way, training a model is cool, right? If you can do it, do it. We also support kind of side loading your own model and adding it next to encoding of other stuff. But the easy solution is that you can build the user vector from as the average of the vectors of the items the user clicked, right? And then the cluster of the clicked items will represent the items that the user is likely to click again, right? If like their clicks are reasonably clustered in that space, where, for example, the time component is interesting, right? So if you also have the time component, then you have kind of a running average of positive interactions that hopefully cluster together, because if nothing else, then let's say the different genders prefer different things usually, and that helps you kind of converge. So there's like very simple solution to that. But like model fine-tuning and all of the above is also valid work. And then maybe one more thing is that on our roadmap, we have a plan to auto-tune the retrieval weights, let's say for a specific user, based on like a click feedback. So then for a given user, you not only have, let's say, a vector average of the clicked items, but you also have for the, let's say, 4 or 5 different signals that you have in your space, basically 5 weights per user, which you could kind of consider to be a ranking model, but not really, because it doesn't just run on the candidates. It constructs the search vector that goes into the whole index and performs like a global query, right? So those are some thoughts in the direction.
How do you suggest embedding models to give you more suggested models for the user
to try? We have for each type of data that you want to embed some kind of default. So let's say you have a text property and a scalar, like a popularity counter. The popularity counter is easy, and for the text embedding, we have a default model there that performs well in most cases. And then the important thing is to try it on your own data, right? So you load the sample of data, and we make it easy to compare the different models. But yeah, same defaults is a good start. By the way, the question was, how do we suggest a model that would perform well for a user? It's a difficult task, yes. Yeah, one resource that I can recommend is there is for at least for the text embedding models, there is a benchmark. So if you go to the MTEB, massive embedding benchmark table or whatever, it changes every week. So you better have some kind of framework that makes you be able to very flexibly adjust and switch models and so on. But yeah, by the way, that benchmark also, like if you are looking at it, take it with a grain of salt, because for sure, at least some subset of those models are training on the test data. So, every time you make a leaderboard, people will try to cheat it, right? So take it with a grain of salt, and the only thing is to test on your own data and on your own task, right? To see the performance. Latency. So for the underlying vector search, you can expect, let's say if you use Redis, you can expect that you can do, let's say, a couple thousand queries per second per box. And the queries will be in the order of like 5 to 25 milliseconds. It depends on the index size, of course. This is for, let's say, millions or tens of millions of vectors per box. And then the database is the good ones can shard. So it's fast. Yes, so if you have a recommendation use case, you don't actually run inference at query time. You basically, because we persist the user vectors as well as the item vectors, so then it's just a lookup. If you have a search query, then let's say A100 can embed 5,000 queries per second. If you have like a reasonable model, if you have billions and billions of parameters, then that's not going to be so fast. But if you have like hundreds of millions of parameters, which is good enough, it's super fast.
Thank you.
Thank you.
Okay, time for the second talk. Hi. How many people from Tabula we have here? Raise a hand. Oh, okay. Make some noise. Good. Okay, stage is yours.
Okay, so slide. Okay, so hi everyone. So today, the topic for today is one of the, I think, most underlooked topics in recommender systems and in machine learning in general. It's called model calibration. This was a joint effort with Betar Spitzer. Raise your hand. The tallest guy in Taboola, I think. And we are both algorithm engineers working for Taboola. So who's Taboola? Taboola is the content recommendation you see at the bottom of articles. So Taboola is a two-sided platform. We have publishers and we have advertisers. Publishers are those sites like Ynet, Calcalist, Bloomberg, The Independent, and many, many more we work with. They provide news for free or any content for free, but they also want to make money. So they allocate dedicated places on their site for ads. And in Taboola, we call those widgets or placements. And we have advertisers who are willing to pay so the ad will show on the publisher site. So here's an example. You can see how the each advertisement look like and some of the advertisers in Taboola. We have Babel, which is, I think it's a competitor of Duolingo, also a language learning app. You have Daily Mail, which is a very shitty celebrity articles gossip app, worse than website, worse than Walla. And we have Toyota, which want brand awareness to show how great they are. So these advertisers, they pay us money every time a user clicks on an ad, and we split the revenue with the publisher. So today I'm going to focus on the advertiser side of the platform, how we can improve their experience. So they pay for clicks, but that's not what they want. They're looking for post-click events. We call them actions or conversions. They can be add to cart, purchases if it's an e-commerce, mobile downloads if it's a game maybe, and stuff like that. But so when creating a campaign, the legacy, the old industry standard was CPC, which is an abbreviation for cost per click. So every time a user clicks a button, an ad, they pay, but we want to make things better for them. So in the past year, and part of the whole ad tech industry that is going into this way, we added more options for advertisers. One of them is target CPA. The CPA is an abbreviation for cost per action. So the advertiser is telling us how much he's willing to pay for one click. And this is how it looks in the Taboola ads site. So they're paying for a click. We take the payment for a click, but they say what's the target CPA that they want. So the way to derive the cost per click, the effective cost per click, given the user an opportunity, we have this and we want to get this. So all we need to do is predict the probability of a conversion given a click. So fortunately, we have a model, deep learning model just for that in Taboola. So let's use it. So I'm keeping this equation here so you won't forget. So let's give an example. Let's say, so we work with Macy's, one of the biggest retail sales in the USA. Let's say they open a campaign to sell Nike Air for men, and they charge $80. So let's dive into their costs. This is imaginary numbers, but they could potentially be close to the real numbers. So the retail price, the price they pay for buying from Nike is $50, and the operating expense, which includes the storage, shipping, maybe $10. So they say, okay, Taboola, we're okay with that if we pay $15 for advertising. So they're keeping $5 as profit, okay? And let's say that we have an opportunity, and we estimate that it should be at 10% for a conversion, but the real probability is 8%. So in this case, so the CPC is $1.50, and they're paying $19 instead. Their average CPA will be $19 instead of $15, and this is bad because their profit will go down from $5 to $1. And why does this happen? Well, it happens because maybe our model knows how to get to differentiate between good users or not, but it doesn't know the true probability. The model prediction is not equal to the probability. So do you know how can I measure that? The difference between those two? Yeah, you're correct. So maybe some of you don't know this, but you're right. So this is called calibration, and we have probability calibration curves to easily visualize the state of our estimator. So we have the perfectly calibrated line we want to reach. This is the dashed line, the y equals x. So, and how is this graph created? So for the x-axis, we take the predictions from our model and we sort them in ascending order and divide the data into buckets. So each point you see here is a different bucket. We have 10 buckets, equally spaced, each of size 0.1. And you can see the buckets here, and the y-axis is the ground truth. What happened, how many conversions we really had in the data. So let's look at, I don't know, this point, for example. So we thought it would be, I don't know, 55%, and we actually had less than 40% conversions. So we are, as you can see, since we are under the perfectly calibrated line, we are overestimating. And advertisers pay more when working with Taboola. Okay, and how do we calculate the error? Because we want to quantify this. Well, we can draw vertical lines to the perfectly calibrated curve and just calculate the weighted average over all the buckets. And this is called the ECE. It's an abbreviation for expected calibration error, and it's 6.2. So on average, we are wrong 6% from the true probability. And I just want to formalize this so we get the hint of it. So to draw a calibration curve or calculate the ECE, we need to choose the number of bins. Not too small, not too big. We can talk about that later, but we need to choose bins, so maybe 10. And let BM be the set of indices of samples whose predictions fall into some bin. So we can define the value for the y coordinate for each bucket and the x coordinate. So the y coordinate is just the average over the indicator function for labels, and the average prediction, just again averaging over the predictions. BM absolute value is the dimensionality of BM, and so I told you, so for each bucket we have the absolute value of the difference, and this is the weight, right? We might have a higher density regions, so it makes sense. So this is the point where, okay, so advertisers have a problem. We know how to measure it, and now we want to improve it. So this is the point where I joined Aviatar, and we started reading papers. So we read a lot, but I think this was the paper that it was published in 2017. I think this caught my eye the most. It's called On Calibration of Modern Neural Networks. And it discusses the reasons why networks are miscalibrated today, at least modern ones. And it reviews all the methods that could potentially alleviate calibration, and also even proposes a new method to do it. So why is miscalibration occurring? Well, here the author observes 4 factors. There could be more, obviously. So we have 4 subplots. The y-axis is mutual for the plot, for all the plots. The error here is the classification error, the amount of samples we get wrong, classify wrong. And the ECE, I told you what it is. If you don't listen, your problem. So, okay, so let's talk about the left graph. We have varying depth. So we take the ResNet, you all know, I hope you do, if not, read. And so we see that the trend is that if we increase the number of layers in the network, the error increases, the classification error, but the ECE has the opposite trend. The same for varying width. Now we fix the number of layers and just change the number of convolutional filters in each layer. And so batch norm, yeah, it's really great. it minimizes the distribution shift from before applying the activation function, and is used in many implementations in hidden layers. But here again, it improves the classification error, but we get worse in calibration. I think the most interesting graph is the weight decay. So we have this sweet spot between under-regularization and over-regularization. And for calibration, the trend is clear. We don't want to penalize more to be more calibrated. And think about it, when you develop neural networks, I usually pick a very small weight decay, maybe 10 to the power of 5, maybe even 0. So that could be problematic. So how do we alleviate this phenomena? So the most simplistic method you can think of is histogram binning. So we need to choose M in advance. And let's assume that the bins are equally spaced. So the first bin boundaries, alphas are the bin boundaries. So the first one is equal to 0, the last one is equal to 1. And we have n plus 1 bin boundaries. And we want to minimize over the squared loss. While this might look frightening, it's not. We are minimizing the thetas. They're just scalar for every bin. So we're dividing the space into bins, and we're minimizing the mean squared loss, this thing for every bin. So if you want to minimize the mean squared error for each bin with a scalar, what is the answer? It's easy. You'll know it's the average of the bin. And the indicator function is here, so we don't include samples that are not from our bin. Everyone here? Okay, good. So what the problem with histogram binning is that choosing the number of bins in advance is hard. You need to know the nature of the problem. It's not so intuitive. So I like better isotonic regression. So this is a generalization of histogram binning. And what we do now is we jointly optimize the bin boundaries and the bin predictions. So now we're jointly optimizing the thetas and also the alphas. So we're solving the same equation, but also minimizing over the alphas. And now we have this monotonic constraint of alphas being monotonically non-decreasing, and also the thetas. So for the thetas, for me, it makes perfect sense since we expect that bigger output from our model will be associated with higher probabilities. So I think that's why it's really good for machine learning. And last but not least, I think, okay, so let's see an example. So this, I just took it from sklearn, so you can search it yourself, but I'll explain it. So we have 100 data points, simulated data points, and we have two fits. We have linear regression, and we have isotonic fit. For isotonic, you can see that what essentially we're doing is dividing the space into bins. You can see that they have a varying size. It's not the same size. It depends on the density, and that's how it looks like. And let's say that I train isotonic regression on a data set. What I get from it, if you apply the sklearn function even, you get the prediction function. The prediction function is just 36 pairs in this example of X and Y pairs. So we have a mapping between the probabilities, the output space and the probability space. And if we get a new sample, let's say here, then we're going to just do a linear interpolation between the two neighbors. And one last method I think is relevant to mention, plot scaling. So here, you probably know it. We take the logits of the classifier and train logistic regression. So Zi is the logits. If you were in a binary classification problem before, then you would have a sigmoid anyway. So basically, we're learning those scalar parameters A and B. So the assumption here is that scaling and translation is enough to fix the calibration error. And this might be too simplistic sometimes. So I think that the most impressive plot in the article is this one, that he took the resident 110 and scored it and saw the ECE on the Cypher 100 dataset. And we can see that even when applying so simple methods like histogram binning and isotonic regression, he improved calibration. So why not go back and fix it in Tabula now that we know how to calibrate? So this was our calibration curve, right? We are overestimating. And this is the curve of the ECVR model. And now let's try flat scaling. So what I expect to happen here is that theoretically, you can think of multiplying by a scalar to make this curve closer to the perfect line. So that's what happened. Not surprisingly, but for some bins, I made the error worse. Like for this bin, maybe. For this bin. So this is working. We're better, but my data set is huge. So why not use a method with more parameters, like isotonic regression? So we did. And now I get an almost perfect curve with an ECE of 0.38 and an error reduction of 93%. So we decided to implement. So like in every machine learning problem, we divide the data into three, train, validation, and test. For the train set, we train our base model, the ECVR model, as usual. And now the trick comes. We generate predictions on the validation set with the base model and feed it to the calibration model. So the inputs to the calibration model are the probability, at least the model output from the base model on the validation set. And it's training on the ground truth of the validation set. So we want to check if we did a good job or not. So we need another test, a test set. So now when we have a new sample, so calibration is essentially a post-processing technique. So we have this, I wrote it as PU, the notation of U is uncalibrated, and hopefully after applying the post-processing technique, which in our case it's isotonic regression, hopefully it'll be calibrated now. To do the trick, I didn't want to add more, do more job in Airflow or scheduling or adding more things to my pipeline. So I just decided to add the layer to my model. So X is the input. We have the regular model. Just append another keras layer. So now we have a fixed ECVR. And how does this layer look like? Well, during training, it's just identity function. Doesn't do anything. And we exploit the callback of keras of the on-train end and use a validation data set to learn the isotonic regression parameters. Now I have this is not my parameters, but let's say I have a set of parameters, a set of X and Y pairs. So now I can just feed back the values to the calibration layer. And now when I infer, it's just a linear interpolation layer. Pretty simple. So we've talked about calibration and why it matters. We've implemented isotonic regression for the ECVR model in Taboola. Well, the calibration metrics have improved, and we have improved the advertising success when starting target CPA campaigns. So everyone is happy, but except from bragging about my work and Vital's work, you can take home something from this lecture. And I think this is the main thought I would like you to take. So calibration is nice, but it can be a total waste of time. So maybe you have a model in production, you're thinking, maybe I should use this, so cool. So maybe not, maybe yes. But I think you need to think about it. Is it relevant for your use case? If you use your output as ranking, for ranking, you don't need calibration. But if you somehow treat your model's output as if it's a probability, then you probably have a wrong assumption, and you need to check what's going on with the calibration. Thank you. And if you have any more questions, you can ask me or Evitar. You can mail us. I think the more appropriate way is LinkedIn today. But yeah, if you're curious, having struggles with calibration, talk to us. Any questions? Okay.
Somehow just they calibrate what they will.
Okay, so I'm not sure I remember everything, but do I take into account the delay between the training time to the real world, like when I really run my model? Is that what you mean? Okay. Oh, okay. Okay, you're talking about that. Hmm. Mm-hmm. Hmm. So when we train our, yeah, you're right. I'm not from the ECVR team, but I'll try to answer. Every time maybe you have an answer, I'm not sure.
You can comment.
Okay, you can come. Well, what I think they do is they just okay. So as time goes on, more and more, the probability of a conversion is less and less, right? So if you take some time window, let's say 1 day, 2 days, then your data is probably valid. I think they assume that the conversions they have counted now is fine, even if we have negative samples that are really are conversions. I think that most of them are not getting thrown away. Okay.
So if we have this trend changing behavior of the customer, if this not to be more sensitive to response to this change.
Can you repeat?
Experience the changes in the user behavior. So we have running CDR and open CDR. Yeah, right. So with this model, we can actually tackle the problem of the spread. You know that in the month we will have lower CDR not because of the cost models, but maybe because of the changes in the.
Okay, so you're saying there's environmental changes, right, from day to day, that could affect calibration. So you're right. This is a component of the calibration error that we don't take into account. We train our model once a day, so we expect that there might be some distributional shifts. But yeah, you're right. The assumption here is that the distribution of the data does not change.
Because you kind of don't know for sure, like the quality of your face or the label is correct. The model is not being sure that it's real conversion, so then it won't be overconfident over basically any type of regulation. Have you done any experiment?
With soft labeling? Or we experimented with regularization. We didn't experiment with different losses or soft labeling. Potentially, they could help, but I think that the reasons for miscalibration were the reasons like from the articles. I'm not sure. I'm not sure what will happen. It could work. I don't know.
Okay, thank you very much. Thank you, Hi. It's also great to see Aviator part of this work. Why data graduates, it's always good to see engaged in this kind of works. Okay, so we have the last talk for today. Uri. Let's check it's working. Okay, it's good. Nice. אני אגיד לך, אין לנו לחץ.
Hi. Okay, so let's start. So just a few words about me. My name is Ori Katz. I'm a PhD student in Balan University, a second year student. I do my research under the supervision of Professor Yoav Goldberg. We are NLP researchers, so we come from the broader domain. I am dealing with, my research is in IR, knowledge acquisition and discovery and exploratory research. I'm not sure that you're familiar with the second and the last term, so we will try to explain it. So let's talk about search. So again, after hearing the last two talks, so whatever I will say from now on, it's based only on one specific feature, which is language. We include knowledge as part of this feature, but we don't have user, we don't have items, and everything is based on the on text, the search and the other tasks. So in search, maybe if it's familiar for some or maybe not, we can describe different types of user behavior or different strategies, and in many cases we can split the different kinds of queries. So the most common one, which is probably the last thing, we don't care about this kind of queries, is a navigational one. Just as people use Google search as an address bar. So they just write Ynet and they use it to link to Ynet. This is the most common queries in Google based on what they published. The second one is the information lookup, which is people ask questions, but those questions are more like close-ended, where someone wants to know a specific answer for how do I get to somewhere, when is something, what is the color of something, and it can be much more complex than that. People can ask multi-hop questions when they want information which is based on different, jumping from different facts. So the whole idea is like fact retrieval or fact verification, question answering, and this is, I think, one of the most major NLP tasks that people are research and also implement in NLP products. And the last one is the exploratory one. So exploratory search, which is there's like it's very debatable, and there's a community in the information research that try to understand what is exploratory search. But the idea is that people ask questions which are more like a small research. They ask questions that there is no one answer for that. It's like an open-ended question. They have many multiple answers that can achieve their task. But maybe it's like an iterative path. They search something, they learn new thing, they want to search, they refine their search, and they do another step. So this is like a journey that the user is doing. And the idea is that the user don't have much information about the topic that he's looking for. So I will show you an example. So if we look about search these days, right? So traditional search engines. So I'm not talking specific like Google or a specific IR technology, but I'm talking about search and IR as a domain. But traditional search and IR are based on term matching. So this is not specifically to lexical matching, but it's also related to semantic matching, like any semantic representation. But the idea is that people, all these tools are optimized to find you the information that's most relevant to your specific query, but based on the terms you are searching. So maybe it's like too vague for you. So let's try with an example. So here is a query. This is a good query for a recommendation system people. But the idea is that we are not looking for recommendation based on users and items here. So if a user asks for a book that explores dystopian themes with philosophical angle, so this query is asking for a very specific long tail attributes of a book. I mean, there's some books are in the world that have some different attributes. People think that they include some philosophical angles, or they are talking about the dystopian themes. The next thing is that this is multifaceted. I mean, there are some constraints on this book, right? They want it to include these attributes. And it's a bit abstract because what does it mean to be a philosophical angle, have a philosophical angle, what is dystopian theme? So it's very abstract query, but it's something that someone can ask, and it's and if we take this query to the new LLM search platform like Perplexity or Copilot, Bing Copilot, that they use, they incorporate search, like they do a search on some index, but they also take this the outputs of the search and do some more complex step where they try to summarize UN answers and write a summary or make it more suitable to your research or exploration. So we can see that they do it pretty well. I mean, we asked Copilot, and we received some nice examples of dystopian books with the philosophical angles, and they also write what is this philosophical angle. So it's like doing more than we asked. So this is Perplexity and Copilot. But when we go to the classic Google search, we don't find anything like that. I mean, if we will scroll down, there is a nice Reddit thread that someone asked this specific question, and it always Reddit to give you the best result, right? But I mean, Google failed to do that, which maybe it makes sense because Google is not working as we want it to be, at least for this part. But those LLM, the Perplexity and the Copilots, they are doing something else for us. They have become the mediator between the index, between the search system and the user. So they are taking the index of the thing that they retrieved by the search system, and they are extracting what they think that we are looking for. But what we actually want as an IR, what actually I want as an IR researcher is that the IR system will do that for me. I don't want an LLM to be part of this process because LLM is very expensive tool, right? I don't want that all the index will be, I don't want it to pass all the index on the LLM when I ask a question. And I don't want to, that the LLM will see only 5 or 10 documents because this is the context window of LLMs. I want that the index will make have the my question, or at least my needs. So we came with this new retrieval paradigm, which the idea is that we want to search document based on specific attributes. And again, those attributes are not like different facets that the user can come with there's no cold start. Everything comes from the text itself. So no one is adding some information about specific book, and then we have like a categorical information about the philosophical angle or whatever. So this should come from the text or from the knowledge of the model. So so the idea is that we want to find we want that every text will represent at least the concept on the object in the text will represent all the attributes of those objects. I will try to be more specific in a second. So as you see, this is a paper published in the Findings of EM&LP with Matan Wetzler, Amir Cohen, and Yoav Goldberg and me. And we call it NER retrieve or NER retrieve, which is like a combination between NER, that I will talk about in a second, and retrieve for retrieval. So what is NER? I'm not sure if any of you are familiar, I guess because it's like a very basic NLP task, but the idea, just to make a reference point, the idea is that named entities are objects in the world that have a name. That's it. So Barack Obama is a named entity, while President of the United States is not a named entity, because there are many of them. McDonald's, it's a named entity, while restaurant is not. So everything that we can call it by its name, dog is not an entity, while I don't know, Lucky or Lucy or a specific famous dog is. So yeah, I took it from the abstract of the meetup, and let's say that I have some commonly people, traditionally people use NER for very basic label or very basic categories, and the idea is that I want for every text that I see, I want to extract in the text itself all the named entity which belong to a specific entity type. For example, I want all the persons in the text, all the organizations in the text, and all the locations in the text. So we do this NER process, and then we have this classification. And the idea is that now we can do things with that. We can do some downstream tasks related to news aggregation, or we want to classify things. We want to find relation between different entity types. So this is like very stable task that people do in industry for many years. I think at least 10 years at NER it's a task, not something new. So here's like an extreme task, extreme case where this is a medical record that you see that almost everything here is been annotated, and you can see that there are things like symptoms and different terms from diabetes and test results and I don't know lots of other entity type. And this example is being used for downstream task to make a unstructured input like text, which is unstructured, into something which you can actually put in a database, or you can do some statistics on, and you can do lots of other downstream tasks. But this is like an extreme case. Yeah. So how do we do NER these days? So again, commonly NER is a token classification task, which means that for each tokens in the input, we want to have a label, which tells us this is for probability, which tells what is the probability of this token to be a part of an entity. So, for example, this text it's in Polish. I don't read Polish, but I know it's said that Asia Bibi comes from Pakistan. Asia Bibi is the name of a person. So we use this transformer architecture, but before transformer we had other things. And then it says bird, but people now use other flavors of bird. But again, this is the same issue, the same idea. And then we split it into subtokens, and it goes into transformer. And in the end, we have some linear transformation on this output, followed by a softmax. So for every token, here you see this token Asia. Again, this is the name of a Pakistani female. So we will have a probability for every class we have, like say person, location, or organization. We will have the probability of it to be the beginning of an entity. So there are some tagging schemes like beginning, inside, and outside. But the overall thing is that the output is that for every token we know if it belongs to a specific entity type or not. So yeah, the question mark should be there. As an NLP researcher, I can tell you that. So how can we use NER in search? So let's take a use case. So for scientific literature research, someone can ask a legit question. So what is the role of the coronavirus in different anatomical systems? So this is, again, I think, a legit research question by a biomedical researcher. And we will use a nice search engine that built by AI2 Israel here. It's called Spike, which is like so in this search engine, everything is indexed by the sentence, and there's beside the sentence itself, there are some nice, interesting linguistic features and relations between terms. So you can build a query. This is in this search engine. You build like a Boolean queries that you can ask for. Like if there is two terms A and B, you can ask, I wanted A will do something on B, and then you can define the relation. So you need to write like a complex queries, but you can do very nice things with it. And another thing is that they offer you the ability to retrieve things that have an entity type of a specific entity type. So here we built this query. It says entity anatomical system, and then I want another term which is coronavirus, and you see this is a screenshot that I took, and you can see that this is like a sentence from papers, scientific papers, and there are hundreds of them, and we know for each sentence where is the anatomical system that the search found. And we can do things with that. I mean, we can now cluster things. We can do statistics about, because we know the exact place where the anatomical system appears, so we can find different relation. and we know now what anatomical systems are related to coronavirus. And I know that like biomedical researchers are using this kind of text mining capabilities. But Spike or other search engines like this are using supervised models, and supervised models are nice, yeah. But the NER categories here are predefined and limited, which means that I don't know, maybe you have 10, 20, 30 different entity types, but we are in a world where people go to GPT-4 and they ask him to write a song in whatever language they want about whatever the topic they ask for, right? So no one is like no one in NLP at least built their own capability on supervised model. And we also know that for every new entity type, like I want now brain regions and non-anatomical system, I need to collect data and I need to train a model. And then collecting data here means like getting it like 15, 20K samples. So it is something that I will not do if I have like just a niche question about anatomical systems and coronavirus. And we also know that NER models are very sensitive to the hierarchy of the entity. So here's an example of an experiment we did. Every column here is like a model that we train. We use DBERTA V large, which is like the off-the-shelf transformer that people use today for a supervised model. So if they don't want to use like decoders only, like generative models, so DBERTA is an encoder. So classification, NER, total classification, people use most of the cases with DBERTA's models. And then we took every column here is a model that we train for 15K examples. And you can see that if we start with animals, this is like animals is the biggest group, and then we go to invertebrate, which like is a subgroup of animals, and then to insects, and then to butterflies. You can see that the precision is decreasing for each step, until a case where butterflies becomes not very useful for us because the amount of false positive will be huge. So if you want to have an NER model for butterflies, we don't have, even if we have the data, it's not possible for us to do. Yeah. Okay. So with that in mind, even the experiment was conducted after we collected data, but for the story, with that in mind, we said, okay, we want to make something new. We want to make search using NER, but we don't want to use the organization person, because no one will ask, bring me text that includes a person, right? It's not interesting. But people will ask, I want to find things about, I don't know, coronavirus and brain regions, or Israeli politicians and Christmas albums, or whatever. So it makes sense that we want that the entity type will be like very complex and very niche, like things that are very rare in the world, like long tail cases. So we collected 500 different entity types. So entity types, again, it's like person, but in our case, it would be like Israeli politician or different proteins involved in the brain, or again, Christmas album, which is like an entity type we have. And then we took 4.3 million Wikipedia paragraphs, and we annotated everything in the paragraph, like every entity for every entity type that we have in the collection. So everything here is silver annotated, which means it's not annotated by a human. Any annotation is very complex for people to do, because you need to know for every entity what it belongs to. So this is silver annotated, but again, this is like the biggest NER data set available today, and the most complex one. And we said, okay, let's see what we can do with it. So you saw the experiment before. This is an example from the data set. So just see the middle one. Here you have this name of a moth, and you see everything is all the titles you have. You can think about it like classes, like labels. So and then this scientist who described this moth, Annette Frances Brown, you see that she have a title of a scientist, and entomologist, which is a scientist who study insects. So yeah, we have like 4 something million paragraphs like this. Okay, so no one in the crowd asked for this, and no one here. But yeah, GPT-4. What about this? When no one used BERT, right? People do use BERT, but what can GPT-4 do? So we said, okay, let's see if maybe the task is solved. Yeah, maybe we don't need all this machinery, and also if we check, just looking on this part where we match like exact and relaxed because it's a generative task. We ask him to generate the name of the entity. So you see the recall for GPT-4 is around 75, which is nice. But the precision here again is very, very low. Why? Because GPT-4 makes lots of false positives, which is these results are replicated for other different papers, other different groups, and other different NER benchmark, which means that we did it correct, and also it means that there is an issue with generative models or with GPT or whatever doing this task. Okay, so let's talk about the task that we actually want to do. And what we want to do is to do a search, right? We want to do a retrieval task. And the idea is that we want to ask for, as a start, we want to ask for the search engine or the IR system that we built. We want it to retrieve all cases, all text that mention a specific entity type. So if again, going back to this literature search, I want to find all paragraph, all the sentence that mention a specific COVID coronavirus, and I want it will also include a brain region. What I'm doing is I'm only using the entity type name, right? I said I want to bring names of dogs. I want to bring names of brain regions. I don't know all the coronavirus strains named. I don't know all the aliases. I cannot construct this list before. So this is the task. This is what I want the system to do. We call this a zero shop type entity mentioned retrieval, but narrative is more catchy. So the experiment is built as a semantic search. I will go very, very fast because I guess that it's something that familiar to everyone. So the idea is that we embed everything. All the corpus is embedded to a text representation. Someone here mentioned MTab. So yeah, again, this is like similar to other IR tasks in MTab. So we embed all the corpus, and then we have this query. The query is just the entity tag, retrieve all the mentions of X, and then we bring the KNN, where the K, I will say it in a second, but the K here is like all the possible documents that we know that are relevant. I will just make it more clear in a second. So the semantic search is, I guess it's clear to everyone, right? Okay, so now I'll try to make it very clear, but I'm not sure. There's a metric called R precision. So some people know it, some people don't. It's like it's a IR metric, but it's been used, I think, from like people stopped using it like only on the last 10 or 20 years. I don't know why. But the idea is that in our precision, we want that to retrieve. We want to find we want to measure the capability of a system to retrieve all the possible relevant documents. So if I'm using like a very famous IR metrics like discount cumulative gain or MRR, so we check the like the top 10, and we said, okay, if it's the order of the relevant document is above the non-relevant. So we don't care about if it's the first or the last. What we do is said, if I have like in this example, I have a query which is the clowns from Sweden. This can be like an entity type. I want to retrieve all the mentions of clowns from Sweden. So I have 350 clowns from Sweden in my corpus. So I said, okay, retrieve 350 and measure how many of the retrieved documents are relevant. So the idea is that here I have like 100 relevant document and divided by 350, and I get 28%. And again, we use our precision when we want to understand if the system can retrieve or be an exhaustive system, or when we want to retrieve everything which is relevant. But the order or the rank is not relevant to us, just the recall or the precision. By the way, this metrics is if you check the precision at k or the recall at k, this is the point where recall at k is equal to the precision at k, because we check how many if there are the k is all the relevant documents, so we check how many potentially how many documents we can retrieve and how many false positives. Okay, so what can we do with it? I mean, we have like very nice text embedding models these days, and again, MTab is it's update every day, and people show very nice things, and OpenAI there, and Cohere there, and Google now joining to this party, and people use like very nice techniques to build text embedding, because I guess many of the community and the industry understand that text embedding, or at least vector embedding, will be the way to do information retrieval, because other IR systems are much more complex to implement. So we took the state-of-the-art open source text embedding these days when we published the paper. Now it's like I think that they are like on the 10 or 20 on the rank, but and also they are all below 1,000 something dimension. There are now like 4,000 dimension, but yeah. And we checked on our tests. So as you can see, the R precision is very low, which means that the system is not it cannot go to production. It's not usable, because if I want to retrieve like all the possible documents, I'm not reaching even the half of that. And we also see that there's no correlation between the number of documents in the text and the performance, which means this task is hard, not just because we retrieve lots of documents. Like for an idea, like we have entity tabs where there are thousands of relevant documents, like films, all the mentions of names of films. So these are the results. Yeah, so the results are very low. So why is it not working? This will be like the last slides. So why is it not working? So I mean, why the state of the art? We saw a supervised model, we saw GPT-4, and we saw the state of the art text embedding. Nothing seems to work. So why is it not working? So we know that IR models are not very good at entities. There is a nice paper from 2021 that shows that if you take, there's a very easy question like where did Barack Obama born, and other entities. So if you compare BN25, BN25 is like lexical matching, it's like TF-IDF. So if you compare it in DPR, it's like the first deep learning based retrieval. It's a dense passage retrieval from Facebook like a couple of years ago. And if you compare it, you see that when the entity is very famous, like Barack Obama, the results will be pretty similar. But when the entity is very less frequent in the data, in the training data, like a Liga Bet soccer player from Israel, so no offense. So you see that BM25 will be as good as it was in the frequent entity, but DPR, like the deep learning models, will just decrease until a case that you just don't find the answers. Another thing is that IR models are very sensitive to the training data. So when you see something in the MTab, just keep in mind that it doesn't say anything about your task. You need to train maybe your own, or at least evaluate your own task and your data. And if you are like very out of domain, if you are using like biomedical data, so don't be like see that the nice results on the common data that it's not very relevant to you. And the last thing is that IR models are optimized for being like a top K models. They are optimized to bring the 10 best results, and we have like the K is like thousands, so it's uncharted water. So just to summarize, so we saw a challenge here that the exploratory search it's a difficult task, not just because attribute, but because it's a hard task. I showed you a new paradigm for different kind of search. It will not solve everything, but it will solve a specific use case, and we think it's a very powerful one. and also show you the limitation of the current technologies. And again, this we just follow the entire machinery of NLP and IR, right? So everything is failing. So it means this is like the task is very hard and it's not solved, and it's maybe interesting. So yeah, the paper is published, the data set is published, and we call the community to join us or not. And yeah, that's it. Yeah, good.
Sometimes, so we have 2 minutes.
Good. Yeah.
We have one.
Oh, come on. Yeah, go ahead. No, I'm joking. Please. So the data set is includes 4.3 million paragraphs. Like a paragraph is like almost 500 something tokens. It's like a paragraph from Wikipedia. We have millions of entities. Like, if you take like a paragraph about Likud party, so you have like names of politicians and names of military people. So yeah, so every entity, not every, but most of the entity will be annotated. It's not have to be Likud, whatever you want. And we have and it's very diverse because we took biology and art and everything, so people can use this data set not for this task or this thing that we care about. They can use it for to train NER for butterflies if they want to, even if it's not working. And there's like a split for IR task and NER, like classic NER for the people who cares about it. Yeah. Sorry, again? No, each entity. There like entities, I don't know, millions of entities. So yeah, it's so think about, there's a paragraph that tells a story of I only think about Likud party, I don't know. So there's a paragraph that tells a story about, I don't know, a famous actor. So the actor is an entity, right? So the actor is, so this entity will have the class of stage actor and a movie actor. Yeah. The reason is, I mean, you don't need more than that. I mean, if you're like constructing a tool, then you need every entity type, right? But we took 500 because we wanted to be like manageable for research. People want to train, or they want to evaluate. So if you have like 2,000, you need to go more evaluation. But again, the idea is that if you can find all the Christmas albums, you can do other things. This is because it's like the edge of the low case.
Maybe there is another set of types.
So
will be more natural. The accuracy of the other models available will be higher. Maybe because of the another methodology, or maybe because of you use really different.
Yeah. So the entity types been we picked them like almost randomly. So we went on a huge list and said, this is interesting, this cannot be published, this is like thing like, a name of a soccer player from Liga, I don't know, TED in Germany. So it's like it's too edgy, but maybe like a Philippine politician, it makes sense. So yeah, we took those, but again, if you manage to do those 500 cases, entity types, you can do everything, because it's not like we pick the thing that interesting just to us. It's we took it's constructed from Wikipedia list and categories, so it's like in every domain possible, I guess. Yeah, it's possible as a solution, but as an NLP and IR researcher, we don't interested in this, because if you have a company that is doing something which is, you don't have a knowledge graph, so you just cannot use it. You want to use NLP because it's possible to do anything, right? Yeah. So yeah.
So, end of the
picture that there were the results were compared to BM25.
Yeah.
My question is, actually, I'm a recommender system guy, but I know that the go-to in this field is hybrid search, combine dense and sparse
Yeah.
methods. So how can you compare with the BM5?
Yeah, so so hybrid search is like a combination between BM25, right, and some embedding space. But so people use hybrid search in production, but for research, you want to split things to be like more pure. You want to understand how BM25 behave, and yeah. But again, yeah. So the results for both of them are very low. So if you will combine them both, I don't think it will be like additive. You don't get like 50%. But I didn't check. But it's not like common when you use hybrid search as a baseline in IR and LP, because it's you don't know what contribute to the result. You want. Okay. Thank you very much.
חיבית המיקרופון. Okay, so thank you very much that you stayed until the end, not trivial, third lecture. We plan the next meetup for the end of May, so stay tuned. It will be at eBay offices, probably, yeah, very likely. Yeah, thank you very much, and thanks again to our host.